forget. Okay, there we go.
Got it.
Now you have to watch what you say because it's recorded.
Oh,
God.
And everyone goes silent.
I know,
Here's our
right? It happens every time.
Yeah, perfect.
All right, Mr. Michael, if you want to share the slides, we can begin.
Absolutely. Oh, you have disabled screen sharing.
Oh,
yeah, you have to just put screen sharing on everybody and just have nobody screen share except them.
I would love to do that. My issue is with on an iPad, I don't have a lot of options. Let me see. I wonder if I can go ahead and switch hosts and it will continue recording for me. Let's try that.
Yeah, give it a shot.
Let's try one thing first. Make host. Yes.
Make me the host.
One day, buddy, one day.
Okay, the recording's still going and you're the host. So
Okay, we got a workaround. Can everybody
That's
see
right.
the document pulled up that says geology?
Earth is
The
logical.
Earth is logical and sands are lazy.
There you go.
There you go. So if you've
Oh.
probably figured out, you not only have myself as another special guest, but an additional special guest. You could call him the extra special guest today, Mr. Colin Price, whom I work with. He's agreed to come and talk to us some more about a little bit deeper dive into some other aspects of geology. Mr. Colin, you want to introduce yourself and kind of give us a background?
Yeah, for sure. Well, thanks for the invite to join your class today, guys. As Michael mentioned, I'm Colin Price. I'm a geoscientist here, currently working at ExxonMobil. So petroleum geology is what I do for a living. But I was trained as in earth sciences at Dalhousie University. They're in Halifax, Nova Scotia, and then did a master's degree over in the UK at Imperial College London, where I focused in on oil and gas exploration, development, and production. So today we're going to talk through some general lessons around geology, some of the fundamentals that you guys can use and apply all over the place, to regardless of what industry or problem you're trying to solve. And then at the end, we'll talk about some oil and gas specific stuff, because that's what I do, and hopefully you'll find it interesting too. In terms of format today, hopefully I'll just kind of give a preamble about the slide and talk through the general point, and then we can discuss. Put your hand up in the Zoom if you have any questions, and of course we'll have a lot of really good discussion.
Cool, thanks, Colin.
All right.
All right.
So also, we will have some activities today that'll let you annotate on the screen, but let's hold the annotation until we've got those activities going, and then you guys can go nuts at the appropriate times. Perfect. So you saw from the title, the Earth is logical and sands are lazy. Those are two of the key lessons that I hope you get out of today's class. Those were told to me by multiple university professors over the years, and they're things that you can lean back on with when you're considering any variety of geology problems, because first, the Earth is logical. It follows a series of set rules that you guys have been learning through your physics, your chemistry, your math, all of that. And so geology is the same. If you understand the mechanisms of what's happening, why things are happening, and how, you can put together a logical argument to explain what might happen next or predict where things are. So geologists, it's our job to understand the Earth's properties and explain the history of the Earth by making observations of the rocks that are exposed at surface, or using remote sensing equipment to understand elements of the properties that are buried deep below ground, and then extrapolate that understanding to make predictions that we then use to identify where resources are, or identify certain risks that could be related to the subsurface that affect people's day-to-day. And then sands are lazy. We'll talk about that more later, but sands are lazy. So before the class, Tara and Mike mentioned that you guys have already talked through the rock cycle. So you're all experts in this already, but since it's so fundamental, I figured we'd talk through it just briefly again. So the rocks start deep, deep below ground, where there's a lot of much higher temperature and pressure than we're experiencing here at the surface, actually enough to make them melt. So that forms molten rocks, magma, which tends to form into these large void spaces where you've got magma chambers that can then either cool in place and form coarse-grained igneous rocks called your granites or your gabbros, or be piped all the way up to the surface through vents and erupt as volcanoes or along deep sea vents or fissures, where you get fine-grained igneous rocks, your basalts or obsidian. So key there is that you have melted out all these minerals into a big soup, and then as you cool or change your pressure and temperature conditions, those minerals will then crystallize out of your magma at a set rate, and in a certain order, depending on what ingredients are available to form the minerals. So when you're looking at igneous rocks, the first thing to look at is how coarse the grains are, or how coarse the crystals are, I should say. So if you've got big crystals, they formed really, really slowly. And so they likely formed deep underground, where a just subtle change in pressure or temperature drove the crystallization. If you've got really, really fine-grained, like so the crystals are so small you can barely see any crystals, then that cooled very fast. And then finally, I see in the chat, Oliver, he's got one that he thinks is obsidian. That's volcanic glass. So volcanic glass, it's something that cooled almost instantaneously. The crystals are so small that it actually behaves like a glass. The windows in your house are actually silica glass, and silica is transparent. So mineral quartz is made of a lot of silica as well. So similar type thing. And of course, White Walkers hate obsidian. We all know that from Game of Thrones. But once we're up at the surface, the conditions that your rocks are going under change. So they're affected to weathering and erosion, transport, and ultimately are deposited again, where they'll lithify into rocks once more. And so the rocks that are made up of small parts of other rocks are called sedimentary. Now, common ones are your sandstones, limestones, or mudstones. Again, here, looking at the coarseness of your grains can tell you a lot about the rocks. So if you have a coarse grain sedimentary rock, it means that those particles haven't been broken down as much. So you likely had it either closer to where those sediments originated, or the grains themselves are made out of tougher stuff and take a lot more to break down. So you can learn some things out of the coarseness of the grains, and also out of the energy of the system that deposited those grains. So think about a river. If you've got a really, really slow moving body of water, or an eddy, or very, very slow moving thing in a river, and you want to go for a swim, put your feet in and it's all muddy and gross. Well, that mud's there because the water's really still. There isn't enough energy to move away those fine particles. In a fast flowing river or in the ocean, where you're constantly pounding and have lots and lots of energy, all that fine stuff gets winnowed away and moved somewhere else. And what you're left with is coarser grained particles. So your cobbles, boulders, sands. So we'll get into this a little bit more later, but you can use the predicted energy of a system and the particles that you're seeing to be predictive of where you might see certain lithologies or certain sands or limestones or muds further out in the system or away from where you are. And so we use those kind of insights in oil and gas to be predictive of where our reservoir rocks are, or where we might have source rocks that the oil comes from.
So, Mr.
What is
Collins,
the,
oh.
sorry.
No, go for it.
What is that? How do you pronounce is that gneiss
Nice.
at the bottom? Okay.
Yeah.
I've heard that term here in Newfoundland quite a lot. Where does that come from?
So gneiss and schist are both metamorphic rocks. So in either things that start as igneous rocks or sedimentary rocks can both be turned into metamorphic rocks when they get buried and and experience high temperature and pressure, again, that forces a recrystallization event. So the minerals that make up a rock are essentially your ingredients, similar to making cookies at home. You've got your recipe card, all your ingredients laid out. You can make a whole bunch of different types of cookies depending on the ingredients that you have. It's the same with metamorphic rocks. So if we started with a sandstone, say, that had a lot of quartz in it and maybe some like biotite micas, if you put that under intense pressure and temperature, then the more unstable elements in those minerals will start to shake off and want to form new crystals that are more stable in that higher temperature and pressure situation. So what you're seeing in schist is it's kind of the first step of that recrystallization. Things kind of reorganize into what we call foliation. Here, let me see if I can annotate on this. So you notice there's a fabric that's kind of running like this through this rock. Those very subtle little lines are essentially all the crystals of a certain type reorienting themselves to be more stable at higher temperature and pressure. Now, if you get even deeper, so like your schists might form somewhere around there. If you get going a lot deeper, that recrystallization happens a lot more aggressively. And so you'll actually recrystallize brand new crystals that on an atomic level are more stable in their mineral structure. So all of this band of really fine stuff, for instance, that's all brand new recrystallization. Took the same ingredients, but they just changed how they're oriented and recrystallized to respond to the conditions that they're in.
Does anybody here know what crystallization is?
Like when something turns into a crystal.
Okay, and what do you think that means? What does it mean to shape into a crystal? Or
Like-
crystalline structure?
Harden over time, I'm guessing.
Okay, like it's got to be cold or
Mhm.
maybe a solid.
It's gotta be a solid.
Could be related to hardness.
Okay, so it's got to be a solid crystal. What does that mean? Does anybody know? Mr. Colin, could you let us know what a crystal is?
I can talk you through that. All right. So
Okay.
what a crystal is it's the best way to describe this. A crystal is formed when a bunch of molecules of a similar type all join together and nucleate around one molecule and grow out in a regular habit. So if we hop down 2 slides, I think I've got one on the rock properties. There you go. Yeah, here you go. So we'll go back to scale in a second, but so crystals are essentially large unions of molecules that grow in that they start growing around one small atom or one small kind of ingredient, and then other molecules will stack around them and grow out in a regular habit. So in this biotite crystal, for instance, it is a joining of these tetrahedral and octahedral layers of silica and aluminum and iron and magnesium interlayered with potassium atoms. Okay, so at certain pressure and temperature conditions, silica, aluminum, iron, magnesium, and potassium are stable when their atoms mesh together and join together into chemical compounds in this particular way. So
That's similar to if the kids make rock candy and
exactly.
stuff at home. Has anybody made rock candy, guys?
No, would have
No.
eaten it.
No.
Were you eating
Has anyone ever
crystals?
eaten rock candy?
Oh yeah, I love rock candy.
Yes.
So you're eating a crystalline structure of elements, minerals.
So,
Sugar.
Great teeth structure.
yeah, if you haven't made rock candy before, you basically start by melting sugar, which is a type of mineral. It's a molecule, right? You melt it and liquefy it. So there's the temperature that Mr. Colin was talking about that is similar to the way rocks form crystals, right? You're just starting with a few different minerals, but you melt it, and under the right pressure conditions as well, the molecules of the sugar crystal align itself in a certain repeating pattern as it cools down, and table sugar turns into rock candy. Whereas in the earth, those minerals can form crystalline structures of different types that kind of look like rock candy.
And the shapes that those crystal structures form at a very, very small level, as the crystal grows, it's what we call a fractal relationship. So how it looks when it's really, really small in terms of its shape repeats up and up and up and grows bigger and bigger and bigger. So if we look at this biotite crystal, for instance, you see the joints in it, these layers, all those planes of weakness are actually those layers of potassium here. The very fine layering that you see in biotite crystals can be explained all the way down at an atomic level. And so
The other
go ahead.
the other thing I think of when you say rock and crystals is I think of like geodes. Would that be a form as well?
Yeah. So
And when
geodes
making geodes.
They're a void space in rock that, remember how I said the coarse crystals take a long time to form, and that's how you get so essentially those geodes are formed when void spaces in rock are filled with really mineral rich fluids, and your crystals precipitate out of those fluids over a long time. So if you find a geode in nature, it'll probably look like an egg, and then you crack it open and you'll have this void space that's been filled up with all these beautiful crystals.
Does anybody have a geode at their house?
Yes.
Was-
But I haven't
Yeah.
broken.
You haven't broken it open?
Man, how can you take the anticipation?
I don't know
Oliver, I
how
think I
she
saw your
takes.
hand raised too.
Also, I have a random rock that I still don't know what it is, but it's there. I was told that was obsidian, but then I was told that wasn't, so I don't know what it is.
All right.
Oh, the refund rock.
Well, if you want to figure out what a rock is in hand sample, you can look at 6 different properties that we got listed here on this slide. So all of these give you clues as to what the rock might be. And if you consider all 6, you can find the unique rock or mineral that matches those criteria. And that's what we use to predict what the rock is. So color, hardness, luster, or how shiny something is, the crystal forms that we just discussed, the density or how heavy it is, and also the cleavage and fracture. So how it breaks can all be used to figure out what kind of rock it is. Yes, Emma?
How would, or like if you went in a cave and you saw crystals like hanging off the side of the wall or on the roof of the cave, how do they stay on there? How do they get hard enough to stick to the roof of the cave?
So as crystals grow, they grow from a fixed point, and then have you ever played that game like Sardines, where one person goes and hides, and then as more people find that person, they just join into the same spot?
Yeah.
That's the same of how crystals grow. One piece of the mineral starts on the wall, and then in caves, it's usually water that's running over that same spot or dripping. More of the minerals that are coming down and being transported by that water join on, and they just make a bigger and bigger clump and how they join on creates the crystal in the crystal form that's coming off. So it's not that the crystal was made and then stuck to the wall. The crystal grew out of the wall over time.
Oh, that's pretty cool. Thank you.
No problem. All right. So let's pop back just one slide, and we'll talk quickly about scale, because that's an important one. All right, so what we've been talking about so far have been things that are very tiny. We brought it back to the atomic scale, how the chemical elements themselves are joining together to make these minerals. Well, even though things happen really tiny and are really important, it's also important to consider in geology all of the different kind of physical scales that we're looking at, and also time scale is very important. So we can look at things at outcrop, which is very large, and see the layers of the rock themselves, how they stacked up over time, and how the structure has changed over time by the flexing of the earth or the uplift associated with rebound after glaciers and all kinds of stuff there. You guys had a plate tectonics class, I hear, and so you understand that the earth isn't static, it's moving around, and all that movement can create a lot of structure in the rock. So outcrops give us keys to understanding that. Hand samples, like everything you've been holding up to the screen just now, those are the smaller samples that allow us to look at the fine details of rocks and understand their properties or usefulness to us. And likewise, from hand samples, we can actually carve very small, thin plates of rock that we look under using high-powered microscopes to look, again, a little bit more deeply at the properties of those rocks and the mineral assemblages that make them up. And so those are called thin sections. So depending on what problem you have at hand, you might want to be looking at the very small scale stuff to understand it, or you might have to go and get your boots dirty and look at an outcrop to understand it. But it's all about whatever problem you have at hand, trying to figure out, all right, what information do I need to answer that problem, and how do I integrate that information together? to come to my conclusion. Another thing that's very important to think about with geology is that rocks are very, very, very old. So there are young rocks like volcanoes. There are rocks being born every day in Hawaii with volcanoes spewing out lava and it's hardening into new rocks. But most of the rocks that we see and walk on are very old. And if we want to understand the processes that made those rocks, we have to take ourselves back and think about what conditions were at that time when they were deposited. And so in my role as a sedimentary geologist for the oil and gas industry, I'm thinking way back in the Cretaceous, way back in the Jurassic and the Triassic, when dinosaurs were walking around and trying to understand where rivers might have been at that time or where beaches might have been at that time. Because those rivers and beaches are now the reservoirs that we're producing oil and gas from offshore. Now, quick side note, oil, you might think it comes from dinosaurs, actually comes from little tiny bugs, little plankton and algae in the ocean. So if you ever go down to a lake and there's that gross algae stuff that you really don't want to swim in, that might be oil and gas someday, the punky grossness. Anyway.
What is the picture right here of with the lighthouse?
So that's Peggy's Cove. It's just south of Halifax in Nova Scotia. And so each one of these pictures that you see, they're all granite at different scales. So at Peggy's Cove, what's been exposed at surface, it's what we call a granite pluton. So if we flip back to that rock cycle slide very quickly. Look at you, there you go. You see that magma chamber there, the big circle? If that whole thing cooled all at once, say the source of heat got cut off from it, then it's buried so deep underground that magma cools very, very slowly. And so since it's slow, creates the bigger crystals, and that's what creates the granite. And then over time, that's uplifted to the surface and then weathered off, and you get a very large area of granite. And so that's what we're seeing at Peggy's Cove.
Cool.
Yeah.
Is that what's mainly Newfoundland made from? What type of rock?
So lots of different types of rocks in Newfoundland, depending on where you are. But here in the local St. John's area, it's a lot of metamorphic rocks. So they were once river or streambed deposits that were laid down in the Cambrian and I think Cambrian period is what most of it is. So billions of years ago. And then it was buried deep underground, enough for the pressure and temperature to make it a lot harder and include all the porosity in it. And then it was brought back up to the surface again as the rocks that we walk on today. So very, very, very old river deposits is what's around St. John's area.
Is this, does some of that have to do with why there's a lot of oil and gas deposits here for drilling?
Yeah, slightly younger, but if you think back to your plate tectonics class, when oceans start to open up as plates are splitting apart from one another, creates what's called a rift basin. And within those basins, you get a whole bunch of sediments that flow into it. So the oil and gas that we're producing offshore Newfoundland is actually from rocks that were stacked up while North America was splitting apart from Africa during the late Triassic and through the Jurassic period. And then later on our margin in the Cretaceous. So as the Atlantic Ocean was widening out, that's when all our stuff was laid down. So the rocks we're walking on in St. John's are actually much older than the ones that we're producing oil and gas from, and they were part of that supercontinent that that the dinosaurs were walking on before the Atlantic Ocean even split apart.
Wow.
Yeah. So,
And that was part of Africa. So basically this Avalon part was once part of Africa.
yeah.
Cool.
Hey, Emma, you got a question?
Yes, I do. You said that your oil comes from mostly the ocean, like little bugs and plankton in the ocean.
Yeah.
Where in the bugs do you get the oil?
So it's organic matter. So the plankton, as they die, fall out and mix in with all the mud and kind of oozy stuff that's at the bottom of the ocean. And as that gets buried and stacked up and then buried deep underground, the organic matter that makes up those plankton gets broken down as it decomposes into what we call kerogens. And so these kerogens then get, when they're exposed to high temperature and pressure, not as much as makes metamorphic rocks, but you're talking like 160 degrees Celsius, you actually cook that organic matter and it cracks into oil and gas
Oh, wow.
and then breaks out of the rocks. So there are actually places over in the United Kingdom that back in the 1800s, they'd take what we call immature source rocks, a source rock being a rock that has enough of that organic matter in it that it has the capacity to make oil and gas. They'd take ones that hadn't been cooked naturally, and they'd actually make these big chimneys down by the beach and go and take a piece of this greasy looking shale mudstone, put it in the fire and cook it themselves, and oil would actually drip out of it. And that's one of the earlier ways that they made oil and gas without even drilling wells. They were just doing it at the surface. So it's interesting stuff. And you might think, where does coal fit into this whole picture? Coal is terrestrial organic matter. So we're all familiar with bogs here in Newfoundland. And if you go into a bog that's been cut into, or like the side of a ditch or something, you can see all the stacks of that root material and grossness. Well, if that gets buried and heated up, that'll turn to coal. And so it's terrigenous organic matter. So really all hydrocarbons they started their journey as organics.
Oh, wow.
Miles, you had a question?
Does Colin actually live in Newfoundland?
I do. Yeah.
I live in Texas.
Cool, man.
Yep.
I've been to Texas a few times. It's nice down there. Okay. If they can just cook it, why do they spend millions on machines to dig it up? That's a great question. And it's a matter of, again, of scale. So there aren't as many places, or there aren't enough places around the earth that have those immature source rocks exposed at outcrop to make enough oil to meet our demand. So we have to go looking for places that we can get a lot of oil out of the ground at an economic rate. So essentially how much we're selling it for exceeds the amount of money that we're putting into to get it out of the ground to meet that demand. So we've got to be very creative in how we look for oil and make sure that we're keeping our eyes open to all the different potential sources of it. So around the world, there's what we call conventional assets, which is where you drill down and produce it out of sandstones that have been buried deep underground and crap. Then you've got unconventional assets where it's in much lower porosity or permeability rocks that you need to actually fracture to get the oil to flow, or you can just shovel it out at surface in oil sands mines where the oil's actually migrated all the way up to the surface. But we're getting pretty specific about oil and gas now, so let's pull back a little bit and talk a little bit more about some more fundamental geology, and then we can circle back and talk about oil and gas as well. You can tell I like it a lot, so I'll talk your ear off about it if you let me. Yeah. Anyway. So we touched on crystallization already. The big principle here being that things that cool fast are very small crystals or fine grained. They cool slow, coarse crystals. And the makeup of the magma itself is very important. So if you start with so you've probably heard the words mafic and felsic before in your previous classes. So
Does anyone remember what they were, mafic and felsic? I know it's been a couple weeks.
Felsic is more iron and silicon, and mafic is more
Yes,
magnesium.
mafic and felsic is.
Felsic is more similar.
Yeah, you know what I mean.
Everyone's already talking. I don't matter.
Yeah, you guys are right. You could say that again. What was mafic again?
Mafic is
Mafic
like
is more
magma.
magnesium or whatever one. Yeah,
Yes, magnesium
right.
and iron combined together, and felsic.
And felsic has
was-
iron and silicon. Or
Yeah,
yes.
I think felsic is the one with the less viscosity. I believe so. Correct me if I'm wrong.
So you guys were onto it there. So felsic magmas, it's a lot more silica. So silica makes quartz. Quartz is just SiO2 is your chemical formula. So silica and oxygen join together and make quartz minerals. A lot of the white or light color that you see in felsic material, that's because of your silica, because just the amount of quartz that's in it. Quartz is actually one of the more common minerals on Earth, just because it's so stable at the pressure and temperature conditions that most magmas form at. You were right on the button with mafic magmas being more rich in magnesium and iron. They're a lot heavier. So remember how we said density of the rocks can be important in understanding what it might be. Iron and magnesium are a lot more dense than your silica and oxygen rich rocks. So where you have more mafic magmas, say volcanoes, mid-ocean ridge, oceanic crust is very mafic rock. The rocks are much heavier than felsic rocks of the same volume. So remember in your plate tectonics class how your oceanic plates go underneath the continental crust? Which one do you think has more felsic material? Which is lighter, continental crust or oceanic crust?
Somebody gonna risk a guess?
I'm gonna say continental.
Wait, are you
Is the
saying,
lighter one.
are you talking about if,
He's talking about the
No.
subduction, when we learned about subduction and how the oceanic crust went underneath. Which one would be heavier, the oceanic crust or the
Oh,
continental
heavier.
crust?
The
oceanic crust is the heaviest.
You got it. You got it.
I thought so.
So now we've made a connection between the actual elements themselves that are making up these rocks and a much bigger process that's actually driving how continental plates move in the world. Something as simple as mafic rocks being denser and having more magnesium and more iron in them is fundamentally one of the reasons why subduction is behaving around the world. So we look at felsic rocks, for instance. They form where your iron and magnesium has already kind of fallen out of your magmas. So if we look at crystallization and how it might happen in a magma chamber, when all the ingredients are still mixed together really nicely in your magma chamber, one of the first minerals to fall out of the mix is olivine crystals. So that's a very mafic mineral assemblage, and so those will form as crystals and perk out of the mix. Now you've got less olivine in the system, and the crystals that have formed but didn't get jettisoned out of the volcano actually settle out into the bottom of the magma chamber. And so what will that result in is actually more felsic magma up at the top, and then more mafic magma down at the bottom. And so depending on when the eruptions happen or at what frequency, you can actually have more felsic volcanic rocks extruded at the surface, or more mafic rocks extruded at the surface.
Does anyone remember which volcano, felsic or mafic, is in Hawaii that doesn't produce lots of the smoke and stuff? It's just
Mafic.
kind of goopy.
Make it.
Mayfic.
Yeah, and then Mount St. Helens, which one's that?
Felsic.
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 Explosive.
Can
right? High
nobody hear
energy.
me?
Got it.
Yeah, the super explosive one. Yeah,
Yeah,
good job,
We
guys.
can hear you, Em.
good one,
Okay.
guys. All right, let's flip to the next slide.
All right.
So we have one special place in Newfoundland that there's only, I think, 3 places on Earth that have ultramafic rocks exposed at the surface. And ultramafic rocks are actually what make up the mantle of our Earth. So in your last class, you learned that we've got our crust, and then our mantle, and then core. So the uplifted mantle at the tablelands in Gross Moor, Newfoundland, is a very important place. And so most of the rocks here that you see, all these orange ones, they are a rock type called serpentinite or peridotite. And that's very, very rich in iron and magnesium, and very, very dark in color. Now, why is it orange? Can anybody hazard a guess? Think about what it's made of. Got
Lava.
Because of
lots of iron in it. Why might it be
Iron.
orange?
What does iron do when it's exposed to the elements?
It
it turns a reddish orange.
oxidizes, oxidization, oxidization.
It
So-
rusts. Yeah. So what you're seeing with it rusting is actually a form of something we call weathering. So rust is what we call chemical weathering. So if we flip to the next slide, weathering and erosion refer to how rocks break down once they're at the surface. So the way that a rock will erode or weather depends on the properties of that rock. So remember how hardness was one of the defining features, as well as cleavage or fracture. So how it breaks and how easy it is to break it will depend, will be real drivers in how it breaks down and what can break it down. So there are 3 main types of weathering. There's physical weathering, where I think all of you guys, being the active kiddos that you are, have participated in physical weathering by breaking one rock against another. The wind and water can also do physical weathering, as well as gravity, with just by nature of rocks falling into
Erosion.
water. Yeah. Second is chemical weathering, where just like oxidation is a good example of chemical weathering, where chemical processes will actually slowly break down the rock. Water running over limestones will dissolve the limestone. That's another example of chemical weathering. And then, like we were talking about with caves and water dripping, that the mineral rich fluids will actually start precipitating out crystals again and making new rocks out of it. And then finally, biological weathering is another one. And that's where nature really bullies our rocks and breaks apart rocks with their root systems, or exploits small cracks and accelerates how things break down. So I've been talking for a long time, and you guys should get an opportunity to annotate some stuff. So let's take a minute or two, and using red for physical weathering, blue for chemical weathering, or green for biological weathering, scribble on these photos as to where you think different weathering processes are taking place. Like what's the mechanism that the rocks are being broken down in all these different photos. Go.
What? Who?
Oh boy. There we go. Don't make me flex my administrative privileges Miss Tara has given me today.
The irony being, he wasn't wrong.
All right, few more seconds. We're getting out of hand.
There you go. All right.
Hey, pie guy.
Yeah, that's enough.
Yeah.
I think that's Miles. Thank you,
Thank you.
Miles.
All right.
Okay, yeah, we got some good guesses there.
This is good. This is good. Does anybody want to explain why they drew what they did on a given picture?
Most of the scribbles along the pictures was me.
I just drew circles, so.
I drew along the beach with red with physical, because I guess that like a lot of people would be kicking up the sand and mixing it around and also putting it into the ocean. But it might be biological.
No, you were
That's
right.
just my guess.
With physical along the beach. So people stepping on the sand, that would definitely break it down. But what else could be breaking down the sand at the beach a lot more regularly than people?
Water.
There you go. Water. Yeah. So sand is actually silica. It's quartz that's been broken down. And since quartz has a hardness of 7, it's much harder than most of the other minerals that are commonly found at the surface. And so it seems to stay behind. And as it gets weathered out, it weathers down to sand and doesn't get very much smaller unless it's really put through some very arduous processes and a lot of time. Yeah. So here, how about another one? Who drew the green over the arch there?
That's also me.
That's also you? Okay, let's get somebody else to raise their hand. Oliver, hop right in, man.
There you go. Oliver, you want to tell us why you drew what you did? Rain, wind, and waves on the arches.
All right.
Okay.
We'll just keep moving along then.
Okay.
Easy enough.
Yep. Fair enough.
So generally speaking, all the scribbles you guys did were right. Big thing that you can take away from this as well is that multiple different processes of weathering can be happening to the same rocks at the same time. And looking at just keeping the aperture open, thinking of all the different things that might be affecting the rocks is important. So good job on that. So flip to the next slide.
I'm going to clear the drawings real quick.
Yeah, we'll clear the drawings.
Yeah.
So after things have been eroded, have been weathered and then eroded, you've got all these little bits that have fallen off. They are transported and deposited again. And so this is the next key lesson of the day. And it's very, very important to understanding sedimentary rocks, if not the most important thing about understanding sedimentary rocks. And that's sands are lazy and they will always go downhill. So since rocks don't have legs and cannot be pushed back uphill very easily by natural processes, they will very predictably always move down. So we look at the sequence of environments that we move from the mountains through flatlands into basins or oceans, lakes, the buckets of the world, so to speak. You're moving from different levels of potential energy and different amounts of kinetic energy through this system. So have you guys ever heard of potential or kinetic energy before?
Yeah.
Seeing some nodding. Yeah.
Anybody remember our rocket class?
No.
Mhm.
Yeah.
Yes.
I think I was in it.
Cool. So if we've got something that's perched high up, but is stationary, that's got a high potential energy. It's got the ability of it to create energy is, well, increased. Once it's, so if we're balancing on the edge of the table, high potential energy. If we've fallen off the table, you've got high kinetic energy while the thing's moving. And then if we're down in the bucket, you've got low potential and low kinetic energy. So if you've got a rock up at the tippy top of a mountain, what does that have? Go. How much potential energy does it have up at the top of a mountain?
Not a lot, because it's just sitting at the top of the mountain.
So it doesn't have a lot of kinetic energy. Does it have any potential energy?
Yeah.
There you go. And so as it weathers, if it gets moved by some wind or water, then it can very quickly translate that potential energy into kinetic energy and move down the system. So as we move down from the mountains, we'll get deposition of some coarse-grained particles at the base of the mountain. And then as more erosion and weathering happens, we'll break those particles down further and transport them along the lower energy systems out into the ocean, or like the final spot of where we're going to be depositing our rocks. So, and in general terms, particles will continue moving so long as there is energy to transport them. So fast flowing water has more energy, and so it can move bigger particles than slow moving water. So if you think about like mountain stream or rivers that are running down the side of a mountain, you tend to see very large kind of blocky rocks making up the beds of those rivers, right? Or in Texas, in the floodplains or washouts out in the desert, you tend to see like these big kind of cobbly rocks all stacked together, because during the flash floods that create those drainages and those rivers, it's a lot of water all at once. It's a lot of energy all at once, and so it can move these big blocky particles and winnow away all the fine stuff. And then once that energy drops, the bigger particles drop out of suspension and fall down as well. So same is true of river systems that are dumping into the ocean. As you hit breaks in the energy of your system, different size particles will drop out of suspension in the water and settle out and be deposited. So you'll have coarser particles along the river, and then fan deposits of these small to medium grained. And then as you move into the offshore, you'll only have very, very small particles moving because there isn't very much energy left behind to move them at all. There isn't enough energy to keep them in suspension in the water. In the very deepest ocean, you actually only have like what we call pelagic ooze at the bottom of the ocean. There isn't any source of sediment that can make it that far out into the ocean. So they're not actually, the muds at the bottom of the deep ocean aren't actually being supplied by the continents anymore. It's only the skeletons and bodies of planktons and other microorganisms that are raining down through the water column very, very slowly that make the sediments at the bottom of the deep oceans. So big takeaway here is that energy can be used and understood by grain size, and coarser grains that you see in rocks and hand sample are usually the result of a higher energy system. Fine grain rocks are lower energy systems and will be deposited only in low energy settings. So quick test time. If I was looking for mudstone, or if I had a piece of mudstone and the particle sizes that are making up that stone are very, very, very small, where might it have come from on this block diagram? Where would muds be deposited? Where could muds be deposited?
Deep sea floor.
The seafloor, yeah. Is there anywhere else?
On the slope
Under
or
the
maybe
sand?
the shelf.
The
of the
lake.
sea.
The lake, yeah.
Maybe
Yeah.
under the sand and the beach.
So the beach would be getting when it have active wave action. So underneath the beach, sure. In a previous time, the ocean could have advanced a little bit higher and been a little bit deeper. But you guys nailed it. The deep ocean and the lake would be spots where a mudstone might be found. Sandstones might be found in the rivers, the deltas, these barrier islands, submarine fans, a lot more localized spots. So yeah, any questions around transportation and deposition?
No, it's pretty neat, and I'll share something that I've experienced since we came up here. The Manuals River Interpretation Center, for those who have access to it here, has a pretty neat demonstration on depositional environments there on the lower floor. So if you're ever there and you kind of walk toward the back of the building, the little hallway that cuts through, it was set up right there, and it's pretty neat to observe, but it demonstrates exactly what Mr. Collins talking about here, how different grain sizes deposit in different areas depending on the energy of the environment they're in. So it's pretty neat.
Yeah, and for those interested, you can actually do an experiment at home around this. If you take in the summer, or take a couple shovelfuls of dirt and put them on the side of your driveway or on the road, and then pour a bucket of water over it, you can see how the particle sizes will actually change as you are close to your bucket, where you're pouring the energy, the water, and it's high energy, versus the further down the system you get, the smaller the particles are, as they all get washed down. All right, I know we're running out low on time here, but we can flick to the next slide. There we go. So we touched a little bit on this already, but yeah, industry applications of geology. Petroleum geologists like myself, we use our understanding of rock properties, weathering and erosion, and especially transport and deposition to try to predict where oil and gas reserves might be found deep underground. So we're trying to place ourselves back in time when these rocks would have been deposited, and use our observations from the wells that we've drilled, using well log data, where you're measuring the radioactivity of rocks, the resistivity of rocks by electrocuting them, or the density of rocks by actually understanding the resonance of the neutron particles in them, to understand the characteristics of those rocks and the lithology of them, and then make predictions about, all right, where in these environments of deposition, where in this system are we, and where do we want to be? Where are my reservoir rocks? Where are my source rocks? And then looking at seismic data over here on the left, I look at pictures like this all day long and try to interpret what the structure might be doing, and then place where I know my rocks are associated with certain layers, which ones might be filled with oil. So yeah, we look at a variety of different data sets, and then try to follow these predictable patterns to solve the puzzle.
Easy, right?
Oh yeah. Yeah, lots of coloring. Yeah.
Does anyone remember when we were talking about seismic waves, which ones are used to see through liquids and stuff? Do you remember the S waves and the P waves, and which ones are used?
Kind of.
Was it the S
I,
wave?
the P, I feel like the P waves could go through your analysis.
It was the P wave.
Thanks.
You know what
So
the P stands
kinda.
for?
Ooh. Remember what S stands for, anyone?
Seismic.
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 No.
Oh,
Remember how they're moving? That was probably a detail that was missed, but
Supersonic.
So there's this kind of wave up here. Those are your P waves. So they're compressional waves.
photonic waves. Oh.
And then you've got shear waves that move back and forth. So best way I like to remember it is, if you're playing with the slinky and you're waving it up and down and it's making the big sinusoid, those are your compressional waves. And then shear waves are if you're taking that same slinky and you're just pushing it back and forth, the bottom of it, and you can see the coils all tighten up and then expand back and come back and forth. All right. So if we flick to the next slide, I'm just going to keep going if we got time.
So I think we did that. Just one more thing. Do you remember which ones we use to realize that we have the inner core is kind of molten, guys?
Wasn't it the S
How did
wave?
we
The S waves.
the F right, it can't go through liquid, right?
Yeah.
So knowing that a S wave can't go through liquid, which one, kind of based on this picture here, do you think we would use for seismic imaging?
P waves.
You got it. So you guys were learning about P waves and seismic in relation to earthquakes. In the oil and gas industry, we use the same physical principles of waves and how they interact with layers in the subsurface, but we use it to create pictures called seismic data. So to make a picture, what we do is we calculate the relationship between when a wave is created at surface from a known source, and then measure the two-way travel time of that wave as it goes into the earth, bounces off a boundary between two different rock layers that have different densities and different velocities that the wave travels through them, and then the reflected energy returns and is measured at a geophone or hydrophone at surface again. And so the length of time that it takes to go down through all the different layers and back, we make estimations of the velocity of certain layers, and with a whole bunch of very, very complicated math, make a picture. And so we can actually see and map the interface boundaries between layers down to 5 and 6 kilometers below ground with about 20 to 25 meters resolution, which is pretty amazing when you think about it. The fact that we're able to see and understand where these structures are without actually drilling a well. Pretty cool. Yes, Emma?
So you basically made a radar to map out where sections of substance or oil is.
Yeah, so
In a
radar is using similar
simplified manner.
principle with waves through the air, where it's bouncing off of a set object and then getting the return signal. But for us, instead of just going through air, your wave is actually going through multiple layers of rock as well. So we have to make assumptions as to the velocity of those different rock layers as well, and fold it into the math that's done to understand that, to translate that two-way travel time back to depth. That make sense?
This is pretty cool. I want to know what a shockwave air gun is.
So
and
air
where do you
guns-
get one?
Yeah.
Air guns are really, really fancy bubble makers. So basically the source that we use is by blowing bubbles. It sends a pulse of compressional energy through the water column at a certain frequency down, that then hits the sea floor, and then a bit of that energy bounces back, and then most of it goes down. The cool thing about air guns, though, is that if you're not sure how much you guys have done about waves, but what's the best way to do this? Do you guys know about constructive and destructive interference for waves?
Mhm.
Yeah.
No.
We touched on it. That's how the principle behind noise canceling headphones. You remember that one?
Sort of.
remember it records the sound and then flips it to the exact 180-degree opposite of the wave, and then it cancels out the noise for your headphones.
It destroys the unwanted frequency of energy that's coming through to your ear.
Yeah.
Oh, that makes sense.
So
Oh, it destroys any frequency that isn't the music that is playing, or what?
yeah. So
Yeah.
with air,
Well, it
with
plays it back in a 180-degree, right?
yeah. So we do the same thing with air guns, except instead of destructive interference, we're using some of that, but we're also trying to make as much constructive interference as possible. So you've got a whole array of air guns that are all putting out bubbles of different frequencies, making waves of different frequencies that are tuned in such a way that they will add up over and over and over to make a very, very strong constructive peak signal. And all of the little chatter side energy is all destroyed using destructive interference. So you're with the source of our air guns, it actually ends up looking like almost like a pipe organ at church. You've got so many guns laid out in a row, and they're all playing at a certain rate and giving a certain frequency, so that they're tuned in such a way that you maximize your constructive interference and get the strongest signal possible to drive down.
I think
Is it just me, or does it seem like there's always oil and gas together?
So that's a really good observation. You're right. So oil and gas are both hydrocarbons, but they are different. What's the best way to describe this? Hydrocarbons occur in nature in a variety of different lengths. Remember how we talked about organic matter and how all hydrocarbons are, at their heart, they started as organic matter. Well, wood has hydrocarbons in it as well, but those are just very, very long chain hydrocarbons. If you draw out the chemical formula for the hydrocarbons that are in woods or waxes or coals, they're very long chain complex hydrocarbons. As you get to what's said lighter and lighter oil, like the oil that's in your car, it is through refining, they've picked out some shorter chain hydrocarbons that are more combustible by mass. So when you burn it, you don't have as much gunk left behind. It burns cleaner, releasing only carbon dioxide and water when hydrocarbons combust. Gas is the shortest chain hydrocarbon. It's just methane, CH4. You got one carbon atom and then your hydrogens all around it, right? And so when you pyrolyze your kerogen and it turns into oil, it's actually a big jumbled up mix of your longer chain and your shorter chain hydrocarbons all together. And it's only over time that the lighter ends and the heavier ends sort themselves out, and the lighter stuff floats up to the top and the heavier stuff goes down to the bottom. And then it stays that way until we poke holes in it and change the pressure temperature conditions, and then it'll actually change. Another complicating factor is that you have your different phases of fluids. So you can have solids, liquids, and gases. And at depth, you can actually have a bunch of gas in solution with your liquids that when you change the pressure, all of the gas will start bubbling out of your liquids. So you can make an experiment out of this as well by going to the corner store and buying a can of soda pop and opening it. And before you opened your can of Pepsi, all of the carbon dioxide bubbles that are making the nice fizzy stuff were in solution with the liquid, but you change the pressure in that vessel by opening it, and all of the gas goes out of solution and bubbles out as well. So in this simplification, it could be that at original reservoir temperature and pressure, your oil and gas isn't actually broken out as free gas and oil. It might all just be a liquid oil column, but as you produce it, the gas separates out of the oil. That was a long-winded explanation.
Hey, Levi, on that same note, do you remember when we learned the carbon chain trick, the methyl ethyl? You remember that?
The methyl ethyl propyl butyl.
Methyl ethyl propyl butyl, right? And do you remember when we talked about gas at the pump, and it's a certain
octane.
octane? Yeah.
Mhm.
Well, how many carbons would that be for
8.
octane? Yeah, so that's what he's talking about, how the methane would be different than a higher carbon chain, right?
Yeah.
And I think gas is also what, hexane? Some hexane?
Yeah, 6.
Yeah. Yeah, that'd be a liquid fraction.
Mhm.
Probably aviation fuel, be hexane.
I know
Yeah.
there's a bunch of stuff in there.
Yeah.
Mixed in there.
We'll get into distillation columns.
Yeah, there you go. So last but not least, we can talk through quickly the elements of a petroleum system that you need for oil and gas. So first of all, you need a source rock. We talked about this a little bit, but those organic rich rocks that the oil actually originates from. Those need to be buried to a deep enough temperature where they'll cook and the hydrocarbon will crack out of it. They then migrate into what's known as a reservoir rock. So these are your sandstones or your limestones that have enough porosity to hold fluid in them. And I know it seems strange that you'd actually have fluid in a rock, but if you're walking around and it's raining, even the sidewalk will soak up a certain amount of water. And so depending on the amount of porosity that you have in your rock, which is like the void spaces in it, and the permeability, which is how well connected those spaces are, you can get a lot of fluid into rocks, up to about 30% in some cases. So you've got very porous rocks that are filled with water until the oil gets in. The oil floats up to the top because it's more buoyant, and the gas above that. But then you need something to seal it in, the top to your bucket, and that's called a cap rock or a seal rock. And so that has very low porosity and very low permeability, which essentially makes it impossible for the oil and gas to move through the pore spaces of the rock. So your really low energy deposits, your mudstones, your shales, those make good seal rocks. So to think back now, what environment of deposition might I get a reservoir rock out of? What high energy environment of deposition might I get a reservoir rock?
Anybody?
All guesses welcome.
Yes.
That's great.
I'm gonna guess a city because you were talking about the sidewalk and the streets.
Well, there weren't cities back in times of the dinosaurs. We want to flip back to the that block diagram.
Yeah, it's not until after the apocalypse.
Yeah, there you go.
Maybe this will jog our memories.
Beaches. There you go. Beaches. That's perfect. And now, where would we get a cap rock? what low energy environment could we get a cap rock to seal all the oil into a beach?
This deep sea floor. Maybe.
Yeah, you got it. And so over time, the sea level has risen and fallen depending on a variety of factors, including plate tectonics. And so if we look at this diagram and we imagine sea level goes out a really long way and your whole system moves forward, you might actually have a beach down here and the ocean down here. And then, so if that's step one, then the ocean transgresses back in again and it floods back over top, just like we're seeing now. And you've got deep water and your muds deposited again in over top of that beach. Those are two elements of a petroleum system. You've got your reservoir and then your cap rock. And so over time, as sea level drops and rises, these environments of deposition will shift basinward and landward over and over and over in predictable ways. And so if I drill a well up here and I see a beach and I see a bunch of ocean underneath it, and I know that the ocean is this way, I might go and shoot some seismic to see what might be out here. And so just very, very rough example of how we can use these patterns that we see in nature and the types of rocks that we're seeing at a given location and predict what might happen next or somewhere else.
Cool. Any other questions, guys?
Will you Kahoot?
Yes, we'll do Kahoot after this. Any other questions for Mr. Colin Price? Everybody's quiet today.
There you go.
I'm trying to think of a question.
We talked in depth. Well, we could do the Kahoot for sure, and everybody's welcome. I don't know, Mr. Colin, are you available some more? I know we kind of went over time.
Oh,
I gotta
have a
run
rock
in
collection. I'll
5
go get
minutes.
it.
Okay.
But
Okay.
let's do a lightning round of, you guys have some rocks to show me, and we can
Yeah.
talk through those real quick.
You want to exit the screen share?
Yep, I'm gonna make you the host again.
Okay.
Is it rocks or minerals that we're
Make me the
showing?
host.
Who's
Make
got
me the
some
host.
rocks?
All right,
Who's got
so-
some local rocks?
All right, Ashford, I'm seeing a red stone set into a ring. And my bet would be that's a garnet. And so garnets garnet is a mineral, and it forms in, you can probably see them in a lot of countertops.
I have rocks. I have rocks.
Oh man, that's amethyst. Nice and purple.
I have.
I know Ashwin's got a whole collection. Ashwin, show some of your cool rocks. I think he showed a Arrowhead obsidian one time.
I don't think, oh yeah.
Oh,
he's
did
still
Ashwin
here.
leave?
No, he's here.
Oh, cool.
I have a.
Oh yeah.
I have
We
no
don't know
idea
what the.
this is.
Don't know what that is. Not
I
through
have
the
a
screen.
small
How heavy is
portion
it,
of
Lexi?
malachite.
It's not really that heavy.
It's a little bit heavy.
It's a little bit heavy.
Yeah, not that much.
I have a small portion of malachite.
Cool.
I don't know what this is.
Lexi and Desi, when you look at that one in the light, is it kind of fluorescent? Like, does it
No.
have any purple or different?
Yeah, there's
Tinges
different
to it?
colors whenever you shine it around in the light.
Okay, that
Yeah, it's
can
very
be,
sparkly.
it can be described as fluorescence.
Oh,
So
And it breaks apart really easily.
Okay, so it's not very hard. It's shiny, so
sure
it's
about
got
that,
a
Howard?
luster.
Yes. It's been chipping off while it's just sitting there. No, don't. Okay, so little bits and pieces break off very easily, but the thing itself does not.
What shape are the bits and pieces that come off?
Like, I don't know if you can really see that, but it's like
Very small, kind of pointed.
Seems like there's a lot of right angles.
Yeah,
So
pretty
would you-
sharp.
Those little bits and pieces, do you think those are crystals?
yeah, possibly.
Yep, I'd say yeah. So
Just not
Some
entirely sure.
sunstone.
I'd say if you bugged your parents to go to the library and get a mineral identification book from the Audubon Society, you'd find out exactly what that is. You got all the tools. You just described the hardness, the density, how it's cleaving, and you've got the crystal form. So
Yeah.
got everything that you need there. Actually, I see the green one up in the corner there.
This
Not sure
is
what that is off the top of my head, some kind of mineral.
this is desert rose.
Desert rose.
Oh, I think there's
cool.
a, Ashwin, is that a fossil?
Yeah,
What fossil is it?
I don't know.
It's like a bone of some sort, like a plant.
Hmm.
I think it's a chicken.
I
Chicken.
have trilobites.
Oh, that's
That
pretty
looks
cool.
like spaghetti, Austrian.
That's gypsum, I think.
I have some moonstone straight from the moon.
Whoa. Oh, fish fossil. That's cool.
It's a sardine, isn't it?
Yeah. Shark
I like
tooth.
this. Yeah, I like the
I
shark
do
tooth.
have some
Oliver, what's that you got there?
I think it's obsidian. I don't know.
Looks like obsidian. Do you see how it's broken? The fractures are all kind of like little semicircles. That's what we call a conchoidal fracture. So it's breaking like glass.
Where's your geo?
And so we know that the crystals are really, really, really fine.
Break them.
And yeah, and those are very sharp when they break. All right, gang.
Awesome.
Well, I got to run to
Yep.
another meeting, but thank you all very much for inviting me to talk today. And
thank you for talking.
Yeah,
Yeah.
appreciate it.
Yep.
Yeah,
Mr.
everybody said
Collin,
thank you to Mr. Colin.
Thank you.
Thank you, Mr. Colin.
Thank you.
Thank you.
And if you
All
have
right,
any other
guys, yep.
follow-up questions, ask Mr. Mike and he'll let me know.
Yep,
Yes.
will do.
Mr.
Thank you so
Mike.
much.
All right,
Mr.
enjoy
Mike,
the
can I do
Kahoot.
Kahoot?
Yep.
Yes.
All right,
Okay.
bye.
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 All right, guys.
I'm gonna log into.
All right,
Kahoot.
does anybody want to show any more rocks? If not, we can start our Kahoot.
I have
I have nothing.
I have this one.
I have
Why don't you guys do that while I get the Kahoot up and running? Sometimes it takes a
I
second.
have garnet. I have garnet from
I think my
Steven
mom just said
Universe.
goodbye to you, Miss Tara.
Who did?
My mom, I think, because I heard goodbye, guys. Or something.
Oh.
This looks like if you like bit into a lollipop and the remains are just.
Oh
right
yeah,
there.
you know.
I have specularite. Spectacularite.
Spectacular light.
It's making me get marks on my fingers. I don't know. If that's a
I'm
good
gonna join
sign or
Kahoot
not.
on my laptop.
I could probably draw with this actually. Let me get a piece of paper. I can't.
All right, can everybody
Cheesy
see it?
music.
Yeah, I can see it.
Yes.
All right, so if you're not familiar with it, again, go to www.kahoot.it and then you put in this game pin. And we'll be talking about some of the stuff we covered today. Mr. Mike, are you playing Kahoot with us?
Oh, he left.
Left.
He left. Okay.
It's time to scream.
Wait,
It got quiet all of a sudden.
Join.
Oh no, I don't want the eye patch.
Or Bob the Cat.
Well,
I am connecting to the Kahoot.
Who's we?
An anonymous player.
anonymous player, no one.
Wait. Can I name myself as Gavin? I thought he used to be in somewhere. Wait, no.
No,
That's
Levi.
true. Emma, could you connect?
Why did it get slower? That was scary.
Yeah.
Just got slower for a second.
You know what, guys? Like when Mr. Mike was the host and y'all, it ran fine. As soon as I connected to my iPad, it froze.
Well, if
Every
you're on
time
an
it freezes.
Might be because you're
Yeah,
on
I'm
an
still
iPad.
connecting. Let me,
I know.
Let me
I'm trying to
reset
fix that
my
solution.
Wi-Fi here.
Yeah, go with a different Wi-Fi.
No, I'll do this.
All right, we got 10.
Just ignore the VPN.
I know, right? But see, Mr. Mike was on the same VPN.
It's that different Wi-Fi.
It doesn't like
Cheeseburger.
Apple products, I don't think.
Wait, what's the PIN?
Yeah, most
I got it.
VPNs have a hard time with Apple products.
576-5117.
Lola, are you Lol astronaut?
Low astronaut. What? Don't even know who that is.
Sure, Lol.
Oh, we got Ashwin singing.
What?
Well, it's not letting me.
Why
connect
does
to
it
the
keep getting
computer.
slow? That's scary.
Come down here, Emma. I'll fix it for you.
Oh, Levi, do you think I'm Bob the Cat? Is that Luck movie you watched?
No, I'm not a Bob the Cat.
Do you think that's who I was?
We're Bob the Cat.
Have you guys watched the Luck movie?
Bro, I wonder who Monkey can be.
I wonder. Is it you?
No.
No, Levi's E.
That's why.
Crush E.
No, I'm Reed.
Oh, I thought you were E. Just E.
All right, who entered twice?
Uh-oh, somebody got on a different
What the-
computer.
No, don't do it.
Oh, wait.
I swear, like,
Yeah, Bob.
I got 10.
hi guy, you better not bot the entire Kahoot.
Guys.
Okay, there we go. It's gone. Oh.
So if there are 3 people that are playing as Bob the Cat, who's called D? One person can be called Bob, one person can be called D, and one person can be called Cat.
I mean,
Okay. Wait, just stay down here. That's why the internet's better right now.
So which one of y'all is called D?
It's Sawyer,
Okay,
Oliver, and
let me
Phil.
know if anyone has not joined yet. Okay.
Miss Tara hasn't joined.
Well, that'd be cheating. I know all the answers.
Canada? Somebody's just Canada?
All right. Representing Canada.
Moose with a moose with
No, but I've seen
pacifier.
Okay, speak now or forever hold your peace. Who has not joined yet?
Me.
my piece is already gone.
no, bro, he's not yet.
All right, we have 11 players. We had 17 on the call.
I'm gonna
Just
put the
making
language
sure.
in Spanish.
It says
That's
13
such a
on the
smart
call.
idea.
Oh, 13. Okay. Some people must have dropped out. All right, 13 on the call. Nobody else wants to join?
Well,
think
you count
Eli
as one of
hasn't
those
joined.
13 people, and
Eli, join.
Eli, are you joined?
Yeah, he's probably away from his computer right now.
Okay, I'm going to start.
Oh.
Who that's from?
Geology
101.
Who's speaking gibberish?
That'd be Eli.
It's that plastic waste, bro.
Bro, that's the plastic waste.
It's plastic waste.
Yeah.
Plastic waste.
I'm on the podium.
Hematite? What's
No, it's pronounced hematite, like the rock.
Oh, okay.
Hardworking people.
Alien spacecraft technique.
Alien spacecraft technique, easy.
How come?
Oh, come on.
How come Ashwin has kept
Alien spacecraft technique. Alien spacecraft technique.
A leprechaun.
The letter 5.
Is that actually a leprechaun?
How come Ashwin
It's a leprechaun. A leprechaun.
leading and then took it off just now? I don't know why he left his camera.
Good job, guys.
Technically,
Letter
the
S.
letter S.
Liquid magma.
21 points behind the person. Ooh. Nearest rock is by the
underworld.
When trees catch on fire, or by the underworld, either one. You choose your place.
I think it's by the underworld.
I'm on the podium.
Small rocks.
Small rocks.
Old age.
Yay.
10 points behind me.
Small rocks. I told you.
Who is
186 points behind Emma, whatever it is, Imakite, whatever you want to call it.
Bro, it's their head.
Rocks feeling the weight of responsibility.
Whoever's named me?
It's rocks feeling the
You have
weight
to
of
respect- you have to
responsibility.
respect
Who
Rocks
is
feeling the weight of
weight of
responsibility.
I don't know. Yeet
Who
is
is
probably
Yeet?
like I bet it's Levi.
I am Levi.
Levi's Yeet, I bet.
Dangerous.
Ice mountains.
Bro. It's dangerous.
Dangerous.
Ice mountains.
That volcano is called dangerous.
No, it's ice mountains. Ice mountain.
Yay.
Yes.
I told you it's ice mountain.
Fourth.
Yeet? Who's Yeet?
Me.
Oh, of course it is. Me. Deep space.
Anti-layered.
Nothing.
Bro, they just disappear. They just poof like that.
It just disappears.
You know that time you accidentally click the right answer first? Earth's crust can move.
First crust can move because it has legs.
Out of town.
Out of town.
Earth's crust can move out of town.
No, by hopping from place to place.
Very quickly.
They like to hop.
Nah, bro,
Very
there's
quickly.
33 questions.
Maybe hopping.
Bro, you can hit the road, bro. Hit the road. Earth's
Who's
crust.
Pie Guy? Oh, I know who Pie Guy is.
Hit the road, check.
I feel like I'm being trailed by like 5 points.
When just load up, I missed one question.
A new beginning.
A new season of Fortnite Battle Pass.
Fortnite Metal Pass.
I have an
No.
answer streak of 10.
I have an answer streak of 10 also.
And
but
I'm
I know
I'm in
I
first place.
Why was I? Oh, I called last because Levi's there.
Smolarization.
Solarization.
No! I clicked the wrong one.
Ah,
You click Ashwin.
Oh my
Oh,
god.
you
bro,
click
I'ma blow up.
downsizing?
Yeah. that's right.
Downsizing.
Ashwin always screams when he plays Kahoot.
you were 10 points
Still stay at
behind me, Levi.
Ashwin though. Like Ashwin.
Disappearing rock.
Happy Rock.
That should be like a game name.
Happy Rock sounds like it could be a video.
If you're broke, and you're not happy.
Rocks
For
are trying
real.
to overcome the world. Happy Rocks, the video game.
Yo, it's them diamonds.
It's diamonds.
Diamonds.
Crystallization.
Bro, you better choose them
It's a
diamonds.
Lulu.
We're in Minecraft now, guys.
Yo, them diamonds.
Diamonds.
Crystallization.
Yo, who doesn't like them diamonds?
Diamonds.
It's crystallization, guys.
Crystallization.
Trash.
It's in the picture.
Trash.
I actually
Yo,
said with
Stop. Stupid.
No. It's actually it's guys. It's trash. It's trash. And lost.
This is true.
It's a lost
Oh,
scuba
no,
diver.
I'm gonna be behind
Scuba divers
you.
are lost. They are lost forever.
Trash.
Okay.
Monkey is making a comeback? What?
Yes. Dwayne the Rock Johnson. Dwayne the Rock Johnson.
Yes. Lightning Smart? No, it's Dwayne the Rock Johnson.
No.
Alright.
Bro, how
Wait.
did you choose Basalt?
Wait. Bro.
Okay, no glass.
When you finish,
Finish your math homework.
No, it's
Yes,
actually if you
sir.
don't finish your math homework.
Finish your math homework. Oh yeah, there's a math website called Do Your Math. Happy, sad,
Happy.
pliable.
No, it's milky or not.
No, I remember
Stubbed
writing this down.
If it's difficult,
Stubbed toes.
It's difficult.
Does it stub
Stubs
toes?
does it stub toes?
Oh, is it minerals caused by paint? Fairy people.
Fairy people.
Paint.
Happy
It's paint. It's paint. It's
Paint.
paint.
Happy
Yo, that went
accidents. Happy accidents. There's a mineral to break on for break point. Break point.
Bro,
No, it's deep cut. It's deep cut. It's deep cut.
it's called breakpoint. Everybody
Yeah, it's break.
I'm pretty sure I got it. I can't do it right now.
Oh. Wow, a lot of people did breakpoint.
Yay.
A lot of people did breakpoint.
Oh. All minerals are
Bad Mama
bad
Jama.
mama jamas.
Bad Mama Jama.
It has to be
Man,
fake.
man, dreams.
You know, all minerals are fake, bro. Who
What's
chose
wait,
Bad Mama Jama?
Some people you like accidentally click it, so I understand. Solid a secret code.
Blobs of slime.
This is the thing that
No, bro.
everyone has
This is a secret code. Dude.
secret code.
Picture's face. It's just hilarious.
Blobs of slime.
Who chose blobs of slime?
Right.
Totally a troll. A troller.
Igneous rock consists of more feldspars and silicon. No, dang it!
Did you just click on Mayfield?
Oh.
Nobody. Magnesium.
Yeah,
rock.
Oswin.
Oh my God.
Oswin, Levi showed me that the voice message you left for him on his phone.
Oh.
Oh. Oh. Oh.
Yes.
Yay!
I wanna pick
Hooray!
him.
Oh my gosh,
in
why does
fifth
I'm so
place.
happy, Oswin?
I'm in 5th place.
3 types of weather.
All right, bro. Who
I
wants
swear to
to
God, if you made me choose the wrong answer. There we go.
They're very good. There we go. NL, Texas.
I mean, red and yellow are both correct.
Big lands of gross more.
We had that exact picture, so I like just remembered it.
Lola, get wrong.
Why? How do you know
Because I want to be second place.
The ocean waves.
No, I don't know that one. It's probably wrong. Yeah.
It's fifth place. I'm on the podium finally. Finally, I'm on the podium.
Friendly.
Everybody listen to this.
That's right.
This is the best.
Let's go.
I'm not silent for a second. Quiet.
Go upstairs.
Dude, what?
Go upstairs.
Oh.
Pure happiness. Magical stuff. Oh. Magical stuff.
I think it's like magical stuff. I'm actually my mouse.
I think it's
Oh no,
magical
I
stuff.
didn't.
Two people said
Pure
magical
happiness,
stuff.
bro. It was pure happiness.
That's
I can't
pure
believe nobody
happiness.
chose that.
Happiness. Hey, Colin, she was helping me. That's my structure. Plants. Minecraft's obvious.
But bro,
It's in the picture. It's in the picture.
How do you spell hobbies wrong?
Oh no.
Yeah, I've passed monkey.
No.
Monkey is now in the dust.
Bro, I just gotta get
Oh,
one more question.
jeez, yo, that's a little dark.
Paper and plastic. Bro, that's why it's it was paper and plastic.
Silicon and oxygen.
Oh, and gas deep underground. A geologist.
A big microscope.
It's extra.
I mean, it's not wrong.
Whoa.
X-ray vision.
Now I want to say sundial measurements, but I don't
Is that a
think
guy?
that's
And
right.
is that a skeleton right there?
Let's go.
Yeah, that's a
Skeleton.
skeleton. That's
Be
a skeleton.
fossils then. Yeah.
Bro, my life is not in danger. I can miss
Whoa,
these
look
next.
at that 31 streak.
I could have had a 31 streak. but-
Uneducated guesses. What?
No, I got it wrong.
Bruh.
Determined by smart
I got it wrong.
people.
Let's go.
I'm still gonna be in like
Determined
first
by
place, though,
smart
because
people.
I have 3,000 more than you.
What's the next
Bro,
one?
I could
Why is yours
Oh, just
Why
click on
is
the
the
first answer that comes up.
You get to play it third.
Mom will not get mad at you.
I picked mom.
Mom will not get mad at you.
Yes.
Bro, I just clicked the first one and got
Mom.
999
Mad
points.
if you lick a rock. Mom won't get
Let's
mad if
play
you lick a
some
rock.
Just
That's
watch.
it. That's the answer.
Yay!
Bro,
it's
I
me.
know.
In second,
It's
it's
for
me.
myself and no one else. Actually, I'll clap for myself, but not for Levi.
My mom won't get mad if you lick a rock.
Yeet.
My mom will get
Levi,
mad if
is that
I'll
you?
just say it's your cause.
Yeah, bro, that was me. I'm yeet. I wish
Good job, Levi. Lola,
I almost
Emma.
won by 4,000 points.
Levi,
and I missed,
Lola,
the
Emma,
last
wow.
two questions.
Actually, be Levi. No.
Good job, guys.
Yeah, so geography is fun because your mom won't get mad if you lick around.
Again, it's telling me to get the Kahoot app, but I have the Kahoot app.
There we go.
It's not reliable.
Yo,
Good
who
job,
is
everybody.
Canada? Who is Canada, bro?
Canada. Oh, I think
Canada
we
was
all
Canada.
know now.
Canada. Everybody says Canada.
Or maybe I could just do like
Hey,
I could be like that.
I'm
that
going
Texan.
to end our recording.
Yeah.